Right, this is solution to 9.7, question 9.7 in the workbook, and this question has changed somewhat. So the solution we ran through in the problem class has been modified in order to simplify the problem. So you can see I've drawn a diagram here. The difference is now is that U out acts along the x direction, whereas previously the diagram in the workbook, that still exists in the workbook, sort of intimates that the air comes out at an angle of 45 degrees along that cone. Obviously then we have a component of momentum in the y direction, which complicates the problem. So it's been reformatted such that now U out is in the x direction, and therefore your area out is going to be the difference between two circular elements, one with a radius of 0.2 and one with a radius of 0.2 plus this distance here. Okay? You need to work out the area out in order to work out the velocity out. Okay? But this is the, otherwise everything else remains the same, all the key dimensions, and this is the new value of force that you are looking for in the x direction. Okay? 2.37 newtons. So before watching me solve this problem, have another go, because now the solution should be far more simple. Okay, the first stage in solving this now, if you're still having trouble, is obviously to do a force balance. And this is very easy because in the question it says that we can assume that the pressure here and the pressure here are atmospheric, so they're equal to 0. Okay? So we want to do a force balance on a control volume along this centre line and up around here. It's really quite simple. Okay? Obviously you can see from the fact air's coming in, it's pushing against the cone. Okay? There's obviously a force here, and the force is coming from this mass flow rate times its differential velocity. Okay, so that's the governing equation. These are the two opposing forces, and obviously they're equal and opposite because this problem is static. Our control volume, nothing's moving here. Okay, so this is what we have. Next stage is obviously this is our unknown, one unknown, which is U out. I'm pretty sure we can find that. Obviously we can work out the mass flow rate using the inflow to our control volume. Okay, we've got the area, we know the fluid is air, and we also know the velocity in, so that should be quite simple. So we can then solve this part of the equation to work out Fx here. Okay, we need to solve for the mass flow, and we can do that for the inflow condition. Very simple. So it's going to be equal to the density of the fluid multiplied by the area in times the velocity in. Okay, if this isn't intuitive, just make sure the dimensions balance. So mass flow rate is kilograms per second. Okay, density is kilograms per metre cubed. That has to go. Okay, there's no length term here. So area is metres squared, that goes. And then obviously U in is metres, that goes per second. So kilograms per second. So this is dimensionally correct. So plug in the numbers, we have them all. Just obviously take some care. So 0.604 kilograms per second. Okay, going back to the original equation, our force balance, mass flow rates multiplied by the differential velocity equals our force. So we know the mass flow rate, we know U in, we now need to calculate U out. In order to do that, we need to work out the area out. Right, to work out the area out, again we have a sort of an annular band. Imagine this this geometry is rotated around an axis, so we have circular elements sweeping around, okay? Effectively two circles, one away from the other. Okay, so if we're looking end on, this is our inner circle, radius of 0.2, and the outer circle is going to be 0.2 plus this distance here, okay? And we're working out that area in there. You can do it 3 or 4 different ways. I always prefer just to work out the areas and take one away from the other. So obviously R2 equals 0.2 plus this distance, okay? Now what we can do okay, so there's our sort of small geometric control volume just for the outlet. All I've done is just rotated that round 45 degrees, okay? So you can just use Pythagoras theorem to work out r squared, which is a number. And where's my solutions gone? Okay, so the larger radius is 0.256. Work those out in terms of two circles, take one away from the other, and you can find the differential area. Okay, which when you work out you should get this number here, 0.081 metres squared. Right, now to find U out, which is our final term, or penultimate term we need to discover. Same equation again, but now in terms of the area and velocity out. Remember, the mass flow rate is fixed. What goes into our control volume goes out the other side. So you can rearrange this expression. We now know A out, we know rho, we know the mass flow rate. Calculate U out. And then the final step, Fx equals our fixed mass flow rate multiplied by that differential velocity. We then get a value of Fx equal to 2.37 newtons.